Europe's Ariane launchers have an impressive track record for reliability. Ariane 4, today Ariane 5, have captured a leading share in launching the world's telecommunications satellites and orbiting European Earth observation or space science missions. But as all launch operators know, every launch remains a challenge. Despite meticulous design and construction, maiden flights carry an even greater risk of failure. And that was the case for the first 10-ton version of Ariane 5 in December 2002. ESA's Comet Chaser had been set for launch just 1 month later. It was to use a different version of the well-proven generic Ariane 5. However, the European Space Agency and Ariane Space jointly decided that it was wiser to postpone the Rosetta launch.
Rosetta is flying on what's called an Ariane G+, which is a derivative of the Ariane generic launch vehicle. Now, the one that failed in December, in fact, was the ECA, which was a brand new launch vehicle. But I think, as with everything in the space business, we have to be prudent, and we try and look for anything that could be a problem that's derived from a failure. And so it was prudent, and the same sort of thing we do in everything in space. We look at every little thing to make sure we're right. And we looked at everything and decided that it was as well to check again and that we couldn't meet the end of January launch window. Obviously, when we change a mission like this, there's all sorts of criteria we have to look at. We have to look if we're going at the same distance to the sun or the same distance into deep space, the thermal constraints that could be on the spacecraft, the amount of fuel we need to get to the new target, if we have enough power on board. And there's obviously a lot of technical constraints we also had to look at on the spacecraft side.
Whilst the satellite was put into safe storage at Kourou, the project and the scientific teams conceived a new revised mission with an alternative cometary target.
We originally had about 9 mission opportunities that we thought would be feasible for a backup mission. And this was rapidly cut down to actually 3, which because of technical reasons, financial reasons, and different other reasons. But out of the 3 mission scenarios we had, in the end, only 1 remained. That was both technically feasible and financially feasible, and last but not least, and very importantly, was also scientifically really challenging and would fulfill all the mission objectives. So we went to the Science Committee in May 2003, and the SPC finally approved the new mission to Comet Churyumov-Gerasimenko with a launch in February 2004.
This comet, discovered in 1969, has an unusual history. Until 1840, at a distance of more than 500 million kilometers, it was unobservable. But that year, passing close to Jupiter, its orbit changed. Another encounter with a giant planet in 1959 brought it much closer, circling the Sun every 6.5 years.
We had right away mounted a very intense ground-based observation campaign to find out what our new object really is. And we looked what was the size, because that's very important. We also wanted to have a comet which is very active. So we determined with observations with the Hubble Space Telescope that the radius of our new target comet was about 2 kilometers. Now this is much bigger than the 600 meters we had for Virtanen. So the next question was, what implications would that have for the lander? Because the lander was especially designed to land on Comet Virtanen. So what we had to do right away to, so to say, go into discussion with our lander team to see if the lander could really land on a bigger object and that it would not be destroyed by the impact.
So the Comet lander team had to quickly reassess the landing system.
The risk would have been that we land at a higher velocity than the landing gear is designed for. In this case, we would run the risk that the lander turns over, and in this case, the mission would be lost. We reconsidered the actual landing gear's performance. We convinced ourselves that 1 meter per second is the limit the landing gear could tolerate, and we finally added a small mechanical part which increased the possible landing speeds up to 1.2 meters per second. The mechanical part which has been added constrains the landing gear's flexibility, adds to its stiffness, and thus allows higher landing velocities.
Overcoming disappointment, selecting a new target, adapting the lander, planning a new journey, and all this in just 12 months required much effort and great tenacity.
During the development itself, we had lots of technical challenges to do a mission as complicated as this. And during this last year, we've also had challenges. I think we've had the technical challenges to make sure we can make the new mission. We've also had sort of motivational challenges. People were a bit down after the launch delay, and we had to get them back up and say, well, we're still going for it. We're going to go to do the same science, a different comet, but it's still going to be just as fantastic. And essentially 1 year's delay in the overall project is really very small.
You know, everybody was used to Comet Virtanen, and it's like I would also always say it's like a forced marriage. People get to know each other, and then they believe this is the most wonderful partner you have. And therefore you had to convince them that we have now a new target and that this is scientifically as great as Virtanen. And some people say it's even better scientifically.
Last October, after a launch readiness review, a second Rosetta launch campaign began in Kourou. The spacecraft's main antenna was remounted, its solar array was deployed for tests, and Europe's comet chaser once again appeared majestic and impatient to set out on its long journey.